Hello everyone, welcome back. Previously, I have introduced the objectives and research methods of microeconomics. In economics, we assume people are rational and always do the best they can to achieve their objectives. So, in the economic models, we usually need to solve optimization problems. Mathematics makes such problems easier to solve. So, in this lecture, I'm going to introduce some math tools that are commonly used in this course, many including derivatives, second derivatives, partial derivatives, total differential, and optimization problems. First, derivatives. This is a fundamental tool of calculus. The derivative of a function f(x) is a measure of the rate at which the value of the function changes with respect to the change of the variable x. In this graph, horizontal axis represents the variable x, and the vertical axis represents y, the value of the function f(x). Along the curve, we can see the value of this function changes by delta y if the variable x changes by delta x. So the change rate is delta y over delta x. And the derivative of function f(x) is to measure this rate when the change in x is a very tiny amount. So it's the slope of the line tangent to the curve f(x). In economics, we often use derivatives to measure the margin, such as marginal cost, which refers to the increase in cost when a firm produces additional unit of goods. It is very useful to memorize some commonly used rules. Firstly, the derivative of any constant is 0. For example, if a function is constant 3, which means the change in x will not affect the value of this function. No matter how x changes, the change in y is 0. Then the derivative is 0. Secondly, the derivative of a linear function is constant and depends on the slope. For example, a function y equals 2x. The slope is always 2. At any point when x changes by 1 unit, the value of y always changes by 2 units. Then the change in y to the change in x is always 2. Then the derivative of this function is 2 at any point. For the power function, the nth power of x, the derivative is n times x to the power of n minus 1. Here are some examples. If the function is x to the 5th, the derivative is 5 times x to the 4th. Similarly, x to the minus 1. The derivative is minus 1 times x to the minus 2. For the logarithm ln x, the derivative is 1 over x. Now, we can combine with the rule for linear function. If a function f(x) is gx times a constant value a, the derivative of f(x) is a times the derivative of gx. Here are some examples. The sum rule means the derivative of f(x) plus gx is the sum of the derivative of f(x) and the derivative of gx. The difference rule means the derivative of f(x) minus gx is the derivative of f(x) minus the derivative of gx. The product rule can be used to calculate the derivative when one function is multiplied by another function, and the quotient rule can be used to calculate the derivative when one function is divided by another function. And last, the chain rule is used for compound function, which means the function of functions. You need to do more exercises to remember these rules. That will be helpful for solving the optimization problems. The derivative of the derivative of a function is the second derivative. The second derivative measures the curvature of the function. If the second derivative of a function at a certain point x0 is negative, then the function is concave around this point, and its slope decreases. If the second derivative of a function at a certain point is positive, then the function is convex around this point, and its slope increases. When there's more than one variable in a function, such as f x1, x2, keeping all the other variables unchanged, the derivative of the function with respect to x1 is the partial derivative with respect to x1. It is usually written as f1 or round f over round x1. When we calculate the partial derivative with respect to x1, x2 is considered as a constant. If the production of a commodity requires multiple inputs, we could use partial derivative to examine how does output change as one of the inputs change with all the other inputs constant. For instance, given a production function with respect to labor and capital, the value of the function y is the output level. The partial derivative of this function with respect to labor shows us how output increases as the firm hires one more unit of worker with a constant level of capital. When all the variables of the function f x1, x2 change slightly, the change in f is the total differential of the function. For example, when the two inputs of the production function, labor and capital, both changes, the impact on the total output can be expressed by total differential. Here, dL is the amount of change in labor, then multiplied by the partial derivative. This product measures the change in total output, which caused by the change in labor. Similarly, the second term in this equation represents the change in total product, which caused by the change in capital. When both capital and labor change, the change in total output is the sum of the change caused by labor and the change caused by capital. Economic models normally assume that economic agents are rational and do the best they can to achieve their objectives. Therefore, we often encounter optimization problems. Now, let's begin with the unconstrained optimization problem. Consider a simple case, a function with only one variable. For example, the profit function, pi, depends only on the output level, q. The firm aims to maximize the profit, so the problem is at which output level the profit can reach the maximum value. This problem could be shown on a graph. The horizontal axis represents the output and the vertical axis represents the profit. In this graph, the profit reaches its maximum when the output is Q star. By observing the shape of the curve around the maximum point, we find that the tangent line of the profit function and Q star is horizontal. The slope is 0. It says the condition for maximizing profit is that the first derivative of the profit function and maximum is 0. Therefore, we call it first-order condition. This condition is a necessary condition to find out the maximum value, but it is not a sufficient condition because minimum point of a curve also should with a 0 slope. To find out whether it is the maximum value or minimum value of the function, it is necessary to examine the second-order condition, that is, the second derivative of the function. At the maximum point, the slope of curve is diminishing, so the second derivative should be negative. Conversely, the second derivative of the function and the minimum must be positive. Then, we can extend the problem to multiple variables case. A function f(x1, x2), the necessary condition for the optimal value of the function is that the partial derivatives of all variables are equal to 0. We can illustrate it by contradiction. Consider a maximum point with the partial derivative with respect to x1 is 0, but the partial derivative with respect to x2 is greater than 0. A positive partial derivative means the value of function can be increased by increasing x2 while keeping x1 constant. So, this point cannot be maximum point. Only when all the partial derivatives equal to 0, the function reaches an extreme value. We have just learned how to solve unconstrained optimization problems. But in economics, the optimization problems are usually with constraint. For example, in consumer's utility maximizing model, the consumer chooses a basket of goods to achieve the highest level of satisfaction. Here, the consumer faces a constraint. The total expenditure of the basket of goods cannot exceed his total income. For constraint optimization problems, we can use the Lagrange multiplier method. If we try to maximize the function f(x1, x2) with the constraint g(x1, x2) equals to 0, we can construct the Lagrange function L equals to f(x1, x2) plus lambda times g(x1, x2), where lambda is called Lagrange multiplier and is an auxiliary variable which can be any non-zero value. When the constraint condition is satisfied, the Lagrange function L is equal to the original objective function f. So maximizing the Lagrange function is equivalent to the original constraint optimization problem. To maximize Lagrange function, the first-order conditions are that the partial derivatives of all variables, including the Lagrange multiplier, equal to 0. If the function has n variables, then there will be n plus 1 first derivatives. The last equation is the partial derivative of the Lagrange multiplier lambda, which is actually the original constraint g(x1, x2) equals to 0. By constructing Lagrange function, we transfer a constrained optimization problem to an unconstrained optimization problem. Well, in this lecture, I introduced some commonly used mathematical tools in this course, hoping to be helpful for your future study. If you want to learn more about mathematics for economics, you can read the mathematical appendix in Variance, Intermediate Microeconomics, or Mathematics in Chapter 2 of Nicholson's Microeconomic Theory. See you next time.